Right. Hello, guys. So this will be your first lecture. So as mentioned in the introduction, we are going to be discussing the three-dimensional geometry in our first chapter, chapter 12. So for the first section, 12.1, it is called the three-dimensional coordinate system, which is how we describe the three-dimensional setup in terms of rigorous mathematical language. Okay. All right. So before introducing the three-dimensional coordinate system, let us go through what we have learned about the one-dimensional and two-dimensional system. So for 1D, the one-dimensional system, it is basically a number line. So a number line is just an infinite line where you can denote each number on that line. For example, you have 0, you have 1, you have -3, and you have 2, and you have root 2. You have every number on that number line, where going to the right means going to the positive axis, and going to the left is going to the negative axis. We usually denote this number line by R. R represents real numbers. Okay? And now let's start defining some notations. So first of all, for a coordinate in a one-dimensional space, we denote by x belongs to R. So x is just a number. For example, you can write 1 belongs to R because 1 is a number, right? You can also write root 2 belongs to R because root 2 is a number, so on and so forth. And there's only one axis, which is this axis, right? As you might imagine, in the two-dimensional system, you'll have two axes. In the three-dimensional system, you'll have three axes, and so on and so forth. Now, what is the distance defined on R? It is defined naturally by this formula. So distance between the point X and the point Y is given by the absolute value of X minus Y. For instance, if you want to calculate the distance between, say, -3 and 2, then it will be -3 minus 2, taking absolute value, which in this case is -5, and then 5, okay? Because you have to go 1, 2, 3, 1, 2 to 2, and that is 5 steps, right? So that's the distance defining on the 1D system. Right. So now after 1D, we have a two-dimensional system, which I assume that you guys have learned in perhaps junior high or high school. So the 2D system is usually described as the Cartesian plane. This noun is not really important. Usually we denote the notation by R2, which is the pairs of real numbers. So specifically, I write x, comma, y to be a coordinate in the two-dimensional plane, R2. So you can sort of look in my notation. I use 0, 1, 2 here, and I use 0, 1 here. So you can see that 0 is representing the zero-dimensional object. In this case, a point and a point. And 1 represents one-dimensional object, which is a line and a line. Since there's no two-dimensional object on the real number line, so I just write 0 and 1. And now we're discussing the two-dimensional system. So there is 0, 1, and 2. Right, so let's go back here. So as mentioned, for a coordinate or a point, we have x and y, a pair of real numbers. For instance, you have 2 and 3 represents a point where the x coordinate is 2, where the y coordinate is 3. So to draw that point on the coordinate plane, you simply draw 2 on the x-axis, 3 on the y-axis, and now you connect those dots, you get 2 and 3. And you can derive a similar algorithm for this point, -4 and 2, right? We cross the two-dimensional axis by x and y, where this point to the right-hand side is plus, to the left-hand side is minus, to the upward side is plus, and to the downward side is minus, okay? So in particular, in this domain, you always have the x-axis for the x-coordinate being positive, and the y-coordinate is also positive, okay? For example, 2 and 3, 2 and 3 are both positive, right? So we usually call this domain the first quadrant, denoted by 1 in the remaining number. And in this domain, you have the x-coordinate being negative and the y-coordinate being positive, meaning that you have minus and plus in the x-y coordinates, respectively. And we denote this by the second quadrant with, again, a Romanian number 2. And similarly, for this domain, we define it by the third quadrant with both the x and y coordinate being negative. And for the fourth quadrant, the x coordinate is positive and the y coordinate is negative. Okay, so these two coordinate axes, x-axis and a y-axis, divide the plane into fourth part, 1, 2, 3, and 4. And those are called the first to the fourth quadrant. So those are the two-dimensional object on the coordinate plane. Now, similarly, we can define a distance on the xy plane. We can define it through the so-called Pythagorean theorem. I'm missing a n here. Right. It is defined naturally in the sense that if we're calculating distance between x1, y1, and x2, y2, those are 2 points on the coordinate plane, right? Then it is defined to be the difference of x squared plus the difference of y squared, and then taking square roots. And it is not that hard to understand this formula. Based on your junior high or high school experience, we know that, for example, if we're considering these 2 points, the distance between them can be calculated by considering this horizontal distance and this vertical distance. So the horizontal distance is naturally x1 minus x2, the difference between the x coordinate. And the distance between the vertical distance between these 2 points will be the difference of the y coordinates. So based on Pythagorean theorem, the hypotenuse will be the square of this plus the square of this and take its square root, right? And that is exactly what we have the formula here. So to be precise, for this example, we're calculating the distance between exactly this point, 2, 3, and minus 4, 2. So according to our formula, we will have, let me use black. Okay. So 2, which is x1, subtract by x2. Be careful, it is minus 4, not 4. Add up with 3 minus 2 squared, and then taking square roots, okay? So in particular, the first quantity will be 2 minus 4, which is 6. You get 36 plus 1. And eventually, you get root 37, approximately 6 in the distance between 2, 3, and minus 4, 2, okay? So throughout this lecture, I would recommend you, whenever I'm talking about an example, you can try to do that first by stopping the video, and then you can see how I do it, right? Generally, it will also be recommended if you guys can read the textbook first, and then go through what I'm teaching about in the videos. So watch the textbook, watch the video, sorry, read the textbook, watch the video, and then do your suggested assignment, right? So those will be the examples. Right. Now, finally, we are in our main object, which I will slow down a little bit. So now we want to define the three-dimensional coordinate system. So basically, it is almost the same as the 1 and 2-dimensional system. The only difference is that now we have 3 variables, x, y, and z. X represents the x coordinate, y represents the y coordinate, and z represents the z coordinate. So instead of a number or a pair, we have a 3-tuple, meaning that you have 3 things in a bracket, x, y, and z. So how do you represent that in a coordinate system? Now you're dealing with 3-dimensional. So you have 3 axes, x, y, and z. So a warning here is that this position are fixed. You always draw x, y, and z. It does not work in a different way. So I recommend you always drawing like this, x, y, and z, right? X, y, and z. Sorry, x, y, and z. Okay, so how do you represent a point? For instance, what is 6 to 4? So 6 to 4 means that you have x coordinate being 6, meaning that your distance, your x distance is 6. So you can see that x distance here is exactly 6. And 2 means that the y distance is 2. So this distance is 2. Okay, you see that this can be projected here. And that means 2, right? We're going to the positive part, 2. Now for the z-axis, z-coordinate, you have 4. So the height of this point is 4. Okay? Right. So let me introduce some notation first, and then we can go back to this diagram. So again, for a zero-dimensional object, the coordinates, you have a point x, y, z belongs to R3. R3 is simply the three-dimensional coordinate system. And now you have three different coordinate axes, x, y, and z. Again, this is plus, this is minus, this is plus, this is minus, this is plus, and this is minus, right? Now, for a two-dimensional object, which is a plane, there's three planes that we are interested about, xy, xz, and yz. So, for instance, what is xy plane? Xy plane is a plane that is spread by the x-axis and the y-axis. So this is called the xy plane, okay? So to be precise, we can actually describe this 4 as a more rigorous quantity. This 4 not only is the height of this point, it is actually the distance of this point to the xy plane. Similarly, 6, which is the x-coordinate, will be the distance from this point towards the yz plane, which is this plane. Okay, this is 6, right? And similarly, for the y-coordinate, it will be the distance of this point to the xz plane. In this case, it is this plane. This is 2, right? Okay, so we have now 3 axes and 3 coordinate planes. Now you can imagine that this 3 planes, xy, yz, and xz, actually cuts the space into 8 different parts. Unlike the two-dimensional case, we don't really name all those 8 octants. In this case, we call it octant because there's 8 of them. We only name the first octant. So the first octant is denoted by the octant that x and y and z are all positive. So for example, 6 to 4 is in the first octant, but -2 to 4 is not in the first octant because the x-coordinate is negative. And we don't really try to name like 2, 3, 4 all the way to 8 octant. Only the first octant is fixed. So that's the difference between the three-dimensional system and the two-dimensional system. Okay. Right. So we have the zero-dimensional object, one-dimensional object, two-dimensional object, and three-dimensional object. Now we can define a distance. So distance between 2 points in the 3D system, P1 and P2, given by the coordinate x1, y1, z1, and x2, y2, z2, is defined, actually it's not defined, it's proven to be this. Distance between these 2 points will be the difference between the x coordinate squared, difference between y coordinate squared, and difference between z coordinate squared. Sum those up, and then take square root. Again, this follows by Pythagorean theorem directly. So you can see that in this proof. Before I start the proof, so in most cases, the proof is not really important in this course. So make sure you understand the example. The proof is not really essential. It is just for the completeness of the course. I will have to prove everything because math is based on a rigorous proof, but it is not really important for the applications. The important part is how to apply the theorems, the propositions, and the examples. Okay. So you see that P1 here is x1, y1, z1. P2 here, x2, y2, z2. So we ought to compute the distance of this red line. And you can do that by this formula. So first of all, this thing can be considered as a hypotenuse of this right triangle, right? Where this part, the horizontal distance, is P2A, is given to be, I make a typo here. This should be x1 minus x2. Right, so that's the horizontal distance. And now how do you compute this adjacent or opposite, depending on your choice of angle? This is actually another hypotenuse of this triangle, right? So first of all, P1, P2 can be understood as P1A squared plus P2A squared plus P1 squared, right? That's the first application of Pythagorean theorem. which is x1 minus x2 squared plus something squared. Now, let something is again a hypotenuse of a right triangle. So P1A squared, in this case, will be P1B squared plus BA squared, right? So this case, this two. So you can see that P1A squared plus AP2 squared will simply be this squared plus this squared plus this squared. And coincidentally, the horizontal distance is x1 minus x2, the vertical distance is y1 minus y2, and the height is z1 minus z2. So you have those three difference squared and add up together. Okay? We can actually generalize this to a n-dimensional space, which is an arbitrary dimensional space. But in most cases, we're only discussing the two-dimensional and three-dimensional space, right? So now we have this is the formula for the three-dimensional space. Let's do some example. So what is the distance between this point 2, 1, minus 3, root 2, and minus 2, 3, 4, root 2? So you simply do the distance is equal to the difference between the x-coordinate squared plus difference between the y-coordinate squared plus difference between the z-coordinate squared, right? And then you take square root. So in particular, the first term will be 2 minus 2, that's 4, you get 16. 1 minus 2 squared, that's 2 squared, so it's 4. Minus 3 plus 4 root 2. Sorry, minus 3 root 2 plus 4 root 2. So that's 1 root 2. So you get 2, right? Okay. So 2 plus 4, that's 6. 6 plus 16, that's 22. You get root 22. So this will be the distance between these 2 points in a 3D space. Okay. Now we not only have a vertical and horizontal distance, you also have a height. So to account that, you have to include this z1 minus z2 squared. Okay, so now we have introduced our 3D system. We can consider some graph of functions on that system. We'll be talking about this more in section 12.5, I think, and also chapter 15. But let's do some simple example for now. So first of all, what is z equals 3? What does this equation means in R3? So just to justify this, the equation z equals to 3 means that all points in the three-dimensional space that satisfy z equals 3. So basically translated into human language, that is saying that we're finding all points where the height of the point is 3, right? Or to be precise, the distance between the point and the xy plane is 3. So what are those? We can find, for example, in the first octant, 1, 2, 3 is a point, right? And also you can find, say, in this case, if we have positive y and negative x, you can write, for example, say minus 1, 3, 3 is also a point, right? Let me put it here. Okay. So basically, all collection of the point that satisfy the height being 3 is a plane, right? It's a plane that is horizontal, that is parallel to the xy plane. So it looks like this. It looks like this. Should include this back here. Okay, I hope that makes sense. So that is a plane that is parallel to the xy plane, and it lifts from the xy plane by 3 units. Okay. Now, what is x squared plus y squared to 4? We know that in the two-dimensional space, in two-dimensional coordinate, this means that all points with distance 2 from the origin, meaning that you are dealing with a circle, right? But in a three-dimensional space, this constraint does not restrict the z value. So for example, we know that 2, 0 being xy satisfies this condition, right? 2 squared plus 0 squared is 4. But now, since z is arbitrary, 2, 0, 2 is on this plane. And again, 2, 0, minus 3 is also on this planar curve. So since z is arbitrary, basically it is a collection of circles making a cylinder. What I'm saying is that, so say this is at the height 3, then this is something like x, y, 3, where x squared plus y squared is 4. So this is always 2 here. Okay? And every kind of z satisfies this equation. So what we're actually drawing is a cylinder, a hollow cylinder. Okay, that's not a good picture. Like that. Okay? So this part of the 3D coordinate system will be the representation of this equation. X squared plus y squared equals to 4 is a cylinder. And it looks like this. It is hollow. All right? Now, lastly, we're asking what is z equals to 3 and x squared plus y squared equals to 4. So as usual, when you're dealing with two equations in the two-dimensional coordinate system, you're basically finding the intersection of those two things, right? Because we're trying to find the point that satisfies this equation and that equation. So in this case, the point must be on both the cylinder and the plane. So in this case, there's only one circle. Let me draw it here. So this is the only circle, xy 3, where the distance is 2. Okay, so this cylinder is infinite of length, okay? You can have the height of 2, height of 100, height of 10,000. But in this case, there's only one circle, where the height is 3, where the radius is 2. So the first object corresponds to a plane, the second object corresponds to a cylinder, and the third object corresponds to the intersection between a cylinder and a plane, which is a circle, okay? Imagine that you cut off a cylinder from half, then you get a circle, right? Okay, the last simple object that we will be seeing is the sphere. So unlike the two-dimensional space, now we have three coordinates, x, y, and z. So basically, this equation, x minus 2, y minus 4, and z plus 1 squared, is the distance between x, y, z, and 2, 4, minus 1, right? To be precise, it is distance squared, because we haven't taken square root. Distance squared. So that simply means that we're collecting every point x, y, and z that has a distance towards 2, 4, minus 1 by a distance of 2, right? If we take square root, that is 2. So to be even more in plain words, you have a sphere with center 2, 4, minus 1 and radius 2. So 2, 4, minus 1, it is somewhere here. 2, 4, minus 1. So if I draw it correctly, it looks like this. This is 1. This is 2, and this is 4. Okay. The y coordinate gives you 4, the x coordinate gives you 2, and you go down by 1 unit. And now we have the radius being 2, so you have the sphere thingy somewhere like this. Okay. Right. So it is a sphere. Why does it give me a rectangle? So it should be like this. Okay. So it is a sphere here. Let me move this one here. Right. So it's a sphere. Every point on the sphere, not on the ball, on the sphere, satisfies this equation. The distance between that point and 2, 4, minus 1, which is the center, is of distance 2. Okay? So that's another simple object that we can describe in the XYZ coordinate system. Okay, so that summarizes what we have done today in this course. We are introducing the three-dimensional coordinate system. And first of all, we recall what we have learned from the 1D and 2D system, where you always have some axis, some sort of quadrant, some sort of distance. So in the 1D case, you have the coordinate, which is a point. You have only one axis. And distance is very simple, defined to be the absolute value of x and y, x minus y. And for a 2D system, you have more objects. For a point, you have x, y, a pair of real numbers. For coordinate axis, you have two axes, x and y. For the quadrants, you have 1 to 4, which you guys should already be learning in high school. And for the distance, we apply the Pythagorean theorem and get that the distance between 2 points is simply the square of x difference and the square of the difference of y, add them up and take a square root. For a 3D case, there's even more objects to discuss. You have three different real numbers representing the horizontal distance, vertical distance, and the height. So a coordinate means you have three different numbers or three tuples of numbers. And you have three coordinate axes, x to this direction, rightward, and y to your direction, and z to upward. So this will be a canonical way to draw xyz axis. And there's three coordinate planes, xy plane, yz plane, and xz plane. Okay. And we don't name every octet, we only name one of the octet, which is plus plus plus. We name it to be the first octet. And we have a corresponding distance, which is also derived from the Pythagorean theorem. Distance between 2 points will be the difference between x plus the difference between y plus the difference between z squared, and then taking square root. And we also have some simple objects that you can describe in the three-dimensional system: a plane, a cylinder, a circle, and also a sphere. We will be coming back to this diagram afterwards because we will be interested in different kinds of surface in 3D space. And to actually draw the surface, you will require some technique, which we will introduce later. So that's all for this lecture, 12.1. I will see you in the next video.